Today we discuss an important example regarding with the canonical transform. Let us consider canonical transform. Q is the function of root over of twice p by m omega sine q, and p is equal to root over of twice m omega p cos q. Therefore we have to find q by p. At first we have to find here we have to find q by p is equal to root over of twice p by m omega into 1 by root over of twice m omega p tan q to evaluate the function q. Therefore we have, just for cancelling root over of twice p, so we get 1 by m omega tan q is equal to q by p. Therefore we have to find here q is equal to tan inverse of m omega into q by p. Now here we have to find the value of capital P. Therefore from the first consideration of the first equation, q is equal to root over of twice p mw by sine q. Therefore p is equal to but here it's an important example that p is related to these two equation explicitly. So here we have to root over of mw by twice p into q whole square plus p by root over of twice m omega by p that whole square is equal to cos square q plus sin square q, that will be 1, which imply m omega by twice p into q square plus p square by twice m omega into p, that will be 1. So here we have 1 by twice p omega, that will be p square by m, plus here it will be m omega square q square is equal to 1. Therefore and just getting in one correction here, it will be root over of twice capital P, it is not small p. So P will be 1 by twice omega p square by m plus m omega square q square. Finally we find. Now here if we consider these transformations, and these transformations we have to prove it is canonical or not at first. It is our consideration to prove this transformation is canonical or not. So for this we are taking the Poisson bracket. Now the new set of variable qp with the old variable qp taking in a Poisson bracket form. So that will be del q del p minus del q del p into del p del q. So separately we find all the values. Now we have del q del q. So here we considering the function q, what happens there. Now taking it equation 1, q is equal to tan inverse of this. So del q del q. That means formula of tan inverse 1 by m omega square m square omega square q square by p square into derivative with respect to q, that will be m omega by p. So after simplifications, p square will be here, so m omega p by p square plus m square omega square q square. Now we have to find del p, where p is this equation. So del p, that will be here for the first part, twice p by 2m omega or omega m, this part only. It is twice p by this, so 2 will be cancelled, so p by m omega. Now we have to calculate del q, del p. So del q, del p will be, q is the function and p 1 by 1 plus m square omega square p square, and here for the differentiation within the bracket m omega q by p, that will be given by minus, that will be given by minus m omega q by p square. Here also another term is p square. So this term will cancel, and finally we find p square will cancel, we find m omega q by p square plus m square omega square. Just a correction, here it will be q square by p square, m omega square q square. We find. Then we substituting all these values in equation number 1 to find the Poisson bracket of Qp. Therefore, Poisson bracket of Qp, if we put this value del q, that will be m omega p by p square m square p square plus m square omega square q square into, it will be del p, that will be p by m omega, minus of this, so it will be plus m omega q by p square m square omega square q square into del p, del q. Here it will be del p, del q. This term is still not evaluated here. From the function del p, del q, that will be, if we considering it, twice m omega square q by twice omega. So omega will be cancelled and it will reduces as m omega q. So del p, del q will be m omega q. Now here we put, yes, del p, del q, that is m omega q. So finally, if we are taking common 1 by p square m square omega square q square, within the bracket we find out here m omega will cancel, so p square, and here it will be m square omega square q square. So both the term will be same, so it will be 1. Since this term is will 1 is converted to 1, so we can say this transform, that means this transform, which transform is given here, this is a canonical transform. So we can conclude here. We can say the required transformation is a canonical transformation. Now we have to find the first generating function, that is f1 concept. Then we consider the terms small p, d small q and capital P, d capital Q to make it a perfect square. Then we substitute the value. Then finally put the value of p and the value of q. What will be the value of p actually? But we can't get, actually we write it is a perfect differential. Now we consider here mwq by p is equal to tan of q, reference to the earlier equation of the question. Therefore we can find here p is equal to mwq or m omega cube by tan q. So here it will be p is equal to m omega q tan q. And we also find capital P. From where actually? So we also take this type of equation, q is equal to, reference to the earlier equations in the question, twice p by mw of sine q. Here it will be m omega q square is equal to twice p sine square q. So sine square q will be p, it will be half of m omega q square cosec square capital Q. So we find small p and capital P. Now we making the product, making the terms as a perfect differential. So we find p dq minus capital P d capital Q. It will be small p is m omega q. Sorry to say, here it is a correction. It is cot q, not tan q. M omega q cot q d small q minus half of m omega q square cosec square q. It will be d capital Q. So if we consider here is an observation. If we take in this way, d of half of m omega q square cot of q, then finally if we break this, first of all if we are taking with respect to small q, then it will be dd q of q square will be twice q, so 2 will be cancelled, then nw q cot q, and after that with capital Q, half of mw q square dd q of capital Q, that will be cot q, the derivative of cot q will be minus cos square q. So here it will be minus cos square q. So adjustment is clear. Now we finally find this type of equation. We can take as a d of f1, where f1 is equal to half of m omega q square cot q. So this is the generating function. We finally find f1 is the generating function. Where is the generating function? And it is also first generating function. And so finally we find this transformation is canonical, and then we can find the how to get this generating function with considering these terms p dq minus capital P dq. So today with the examples we can clear how to apply the canonical transform, and as well as how to get the generating function.